Okay, so this is a recording now. I apologize again for starting late today. That was a technical thing that I had not come across before. As our speaker, it's a pleasure to have Kiwamu Watanabe from Chuo University. He is going to talk about positivity of exterior power of the tangent bundle.
Thank you very much. And first of all, I'd like to thank the organizers for inviting me to this nice seminar. So today I want to talk about my recent works on the positivity of the exterior power of the tangent bundles. So let us start from the review of the history of the problem. So in my talk, I always assume that the variety is a smooth projective variety defined over the complex number field, and we call it a projective manifold. And the story begins with the Morris solution of the Hudson conjecture. So what he proved is, if the tangent bundle Tx is ample, then X should be the projective space. And I remarked that the tangent bundle is called ample if the tautological line bundle associated to Ptx is ample. And as you know, this result is very important in the history of algebraic geometry because this was the starting point of the minimal model program. So a lot of guys have been trying to generate this result to a lot of directions. And one of the generalization of this theorem, Campana and Petane posed the following question in 1991. So what they want to do is to replace the ampleness by neffness. So if Tx is neff, then what is X? So this is a question. And by the same way as the ampleness, so we may define the neffness of the tangent bundle as follows. So if the tautological line bundle associated to Ptx is neff, then we call the tangent bundle neff. And so related to this question, actually Campana and Petane gave a complete classification of project threefolds with neff tangent bundle in their paper. And I think related to this question, I think there are three natural questions. And the first question is, what is a natural candidate of project manifold with neff tangent bundle? And then a natural candidate is a homogeneous manifold. So let us consider projective manifold, projective homogeneous manifold, and so say X, and take any point P on X, and then so we have a homogeneous manifold, and there is a point P, and take any tangent vector at the point. Then this tangent vector can be extended to the whole space by using the transitive action of homogeneous manifold. So it means that any tangent vector at the point can be extended to the vector field. So it means that any homogeneous manifold admits globally generated vector tangent bundle. So it means that any homogeneous manifold admits neff tangent bundle. So this is a homogeneous manifold is a natural candidate. And furthermore, it is well known that such manifold homogeneous manifold can be expressed as a product of an abelian variety and rational homogeneous manifold. And the second question is, so are there some other examples? The answer is yes. Actually, so let us consider an elliptic curve C and take a semi-stable bundle E of rank 2 on C. Then consider the projectivization of the bundle E, which is denoted by PE here. And then it's easy to check that its tangent bundle is neff. Okay, so of course this is not homogeneous. So there is a example of project manifold with left-tangent bound, but not homogeneous. And actually, there are a lot of this kind of example. And the third question is, then can we get some structure theorem of project manifold with left-tangent bound? The answer is also yes. Actually, Dumais-Pétanet-Schneider proved the following theorem in 1994. So let X be a project manifold with left-tangent bound, then what they proved is there exists a finite ether cover F from X tilde to X such that the Albanese map is a locally trivial fibrillation. So this means, this is a smooth morphism. And any fiber is isomorphic to a fixed smooth funnel F with left-tangent bound. So by this theorem, so roughly speaking, a project manifold with left-tangent bound is up to an ether cover. A project manifold with left-tangent bound is algebraic fiber space over an abelian variety whose fibers are funnel with left-tangent bound. So if we know the structure of smooth funnel with left-tangent bound, then roughly speaking, we know the whole picture of the structure of project manifold with left-tangent bound. And furthermore, the Dumais-Pétanet-Schneider also proves the following. So let X be a project manifold with left-tangent bound, then any contraction of Kx negative extreme array is a smooth morphism. So I think this is a very strong condition. And I also remarked that so they proved this theorem, but the proof contains some gaps, and it was fixed by Solakonde and Wisniewski in 2004. And today I have not enough time to explain how to prove this, but basically the most important point is, so by the nearness of the tangent bundle, we know that any rational curve is free. So what is free? So for a rational curve F, F or its image FP1 is called free if the F probability X is F as a vector bundle. So under this condition, we know that H1 of F probability X vanishes. So it means that this rational curve can be moved freely. So this is a definition of the free of rational curve. Okay. So going back to this theorem, as I said, I think it's natural to ask the structure of smooth funnel with left-tangent bundle. So related to this, Campana and Pétanet pose a following conjecture, which is a so-called Campana-Pétanet conjecture. So the statement of the conjecture is the following. So every funnel manifold with left-tangent bundle should be homogeneous. So this is a conjecture. And I remark that this conjecture holds 4 dimension at most 5, but this is widely open in a higher dimensional case. So these are the history of the project manifold with left-tangent bundle. And so let's go into the case of exterior power of tangent bundle. So as I explained, Mori proves the Hudson conjecture, and so corresponding to the Hudson conjecture, Cho and Sato study the project manifold with ample second exterior power of the tangent bundle, and actually they prove that such manifold should be a projective space or smooth quadratic hypersurface. Okay, and as I said, Campana and Pétanet gave a classification of projective threefold with left-tangent bundle, and then they also study the threefold with Neff second exterior power of the tangent bundle. Actually, they prove the following. So let X be a threefold and assume that the second exterior power of the tangent bundle is Neff, but Tx is not Neff. then there exist two exceptional cases. The first exceptional case is the blow up of P3 at a point. And the second case is a final threefold of index 2 and Picard number 1, except for those of degree 1. Okay, so this means that if the variety admits next second exterior power of the tangent bundle, then in almost all cases, the tangent bundle should be also net. But there are these exceptional cases. So based on these classical results, I want to consider the following problem. So if some exterior power of the tangent bundle is net, then I want to know the structure of X. And today I want to focus on the case when R is equal to 2. So what is known about this problem, except the previous two results? So when R is equal to 2. So for instance, there are the following four results. For instance, Kazunori Yasutake, who was a student of Sato, he studied Fan fourfold case and Fan n-fold with birational contraction case. And toric case was studied by Schmitz. And for some more strictly net case was studied by Lee, Wu, and Yang. Anyway, so there's some known results. But one of the motivation on my today's talk is to give a generalization of these results. Okay. So now is the time to go to the main results. So as before, I always assume that X is a projective manifold of dimension n, defined over the compressed number field, and assume that the secondary exterior power of the tangent bundle is net. Okay. And then the first main theorem, which is called Theorem A, is the following. So the first assertion is if X admits a birational contraction of a Kx negative extreme array, then X should be the blow up of the projective space at a point. And the second assertion is otherwise any contraction of a Kx negative extreme array phi is a smooth morphism. So the second statement seems some analog of the result by Dumaire, Petano, Schneider. Okay. So this is the first theorem, Theorem A. And by using this, the second theorem, Theorem B, is the following. And if X is rationally connected, then X should be a Fan manifold, such that the Kramer-Mori cone is a simplicial cone. As you know, in general, Fan manifold is rationally connected, but in general, the compass does not hold, but in our case, it also holds. So this is the second theorem. And so to prove this Theorem B, we need to use Theorem A. I will explain later. And so by using Theorem B, we can get the following Theorem C. So Theorem C states that if Tx is not Neff, then X is a Fan manifold. Okay. So these three results are the main results of my talk. And for some more, by using these three results, we can obtain two corollaries. So the first corollary is we can get a generalization of Schmitt's results. So as I said, Schmitt studied our problem in the case when the variety is toric, but we can generalize his result to the toroidal spherical case. So the following is a corollary, D. So if X is toroidal spherical, then X is rational homogeneous or the blow up of the projective space at a point. And for some more, we we can also get a higher dimensional analog of the result of Campana and Petane as follows. As I said, as I explained, so they classified three folds with next second extra power of the tangent, but we can generalize, we can get a higher dimensional analog. I actually let n be at least 4 and at most 6. Then if the x is not net, then we have two exceptional cases as follows. The first case is the blow up of Pn at a point, and the second case is a funnel of pseudo index n-1 ethical number 1. So this can be seen as a higher dimensional analog of the result of Campana and Petane for the three folds. So we can get these two corollaries. So by the way, so we can get, so these five results are the main results of my talk. But today, in the remaining time, I will explain how to prove theorem A, B, C. Okay. So any question or comments? Okay. Okay, so then let's go into the proof. So in the proof, we need to use the deformation theory about rational curves. So let us recall the definition and some basic properties of families of rational curves quickly. Okay, so let rat curves and x be the normalization of the locus of rational curves in Chow x. So more precisely, so let us consider the Chow scheme Chow x, and then consider the locus of all rational curves in Chow scheme. Then so this admits a scheme structure, so take the normalization. So it is nothing but the lat curves and x. So this notation is appeared in the book by Corral, entitled Rational Curves on Algebra Variety. So I employ his notation. And then an irreducible component M of lat curves and x is called a family of rational curves in my talk. And furthermore, associated to a family of rational curves M, we can construct a universal family like this. And by construction, we can check that this P is a P1 bundle, and this Q is nothing but an evaluation morphism. And then, so under this notation, so let M be a family of rational curves. Then M is called a dominating family if the evaluation morphism is a dominant morphism. Okay, so and this is equivalent to the condition that M contains a free rational curve. This is well known. And furthermore, M is called a coupling family if Q, this evaluation morphism, is surjective. And finally, M is called an unsplit family if M is proper as a scheme. So I will use these notations in my talk. Okay. Okay. Then so I have two remarks. The first remark is the following. So for a kx negative extremal lay R, consider its contraction associated to the lay R, which is denoted by contour R, and assume that this guy is of birational type. Then it's easy to check that any rational curve C in the lay R is not free. So this is very easy actually. So take a family of rational curves M such that M contains C as a member. Then any M curve is numerically equivalent to each other. So we have the locus of the M curves are contained in this exceptional locus. This E means exceptional locus of the birational contraction. Okay. So this means that the locus of the family is not dense in X, thus M is not a dominating family. But as I said, so this dominating family, M is dominating family if and only if M contains a free rational curve. So this means that she is not free. Okay, so I will use this later. And furthermore, the following is not trivial. This is very important. We have the following theorem. So let M be an unsplit covering family, then you can consider the rational chain connected fibration with respect to the family M. And furthermore, we assume that any M curve is free, then the rational connected fibration is a morphism, and furthermore, we see that it is a smooth morphism. Okay, so this corresponds to the result by Dumari-Pétain-Schneider, and actually by using the proof of the Dumari-Pétain-Schneider on the smoothness of the contraction of the project manifold with an F-tangent bundle, we can prove this. But basically, this result is, I think this is a result of Kanemitsu. Anyway, I will use this, right? Okay, so let's go to the review of the fundamental properties of manifold with next second x to the power of the tangent bundle. So the framework is the same as before. So let X be a project manifold and assume that the second x to the power of the tangent bundle is net. Then, yeah, it's very easy to check that the anti-canonical divisor is also net. Actually, this follows from this equality. That is, so namely, so if you take the determinant of the second x to the power of the tangent bundle, then it should be the same as 1 minus n powers of omega x. But now we assume that the second x to the power of the tangent is net, so the determinant is also net. So it's the anti-canonical divisor. So we know that our variety admits net anti-canonical divisor. So this is a lemma 1. And the second lemma is the following. The second lemma is also very easy to check, but this is very essential in our proof. So let she be a non-free rational curve, then the anti-canonical degree of the non-free rational curve, she is at least dimension of x minus 1. Okay. So this is a very strong condition. So let us check this quickly. So let us first take the normalization of she, which is denoted by f here, and then consider the f fullback tx, so which is a vector bundle over P1, but as you know, so any vector bundle over P1 is a direct sum of line bundles by Grothendieck's theorem. So it means that there exist integers, AIs, such that f fullback tx is isomorphic to this guy. And here we may assume that AI satisfy these inequalities. And then we can check that AN is negative and A1 is at least 2 because, as I said, we assume that she is a non-free rational curve. So it means that f fullback tx, this guy is not net. So this means that AN is negative. And furthermore, although we consider the normalization of she, which is f, and then take the differential of f, then this differential should be the inclusion. Then TP1 is O2. So from this, we know that A1 is at least 2. Okay. So we have these two inequalities. And then, so take the second x to the power of this guy. And then this is nothing but this one. And from our assumption that the secondary exterior power of the tangent is F, we see that an minus 1 plus an is non-negative. Okay. Then we know that an minus 1 is at least minus an. And furthermore, as I said, n is negative, so minus an is positive. Okay. Okay. So as a consequence, we have the following. So as you know, the anticanonical degree of the rational curve C is nothing but the summation of AIs. So this is equal to this guy. And furthermore, from here, we know A1 is at least 2. And furthermore, as I said, an minus 1 is positive from here. But additionally, we have these inequalities. So A2, A3, n minus 2 are positive. So this means that this part is at least n minus 3. And furthermore, from this, we see that an minus 1 plus an is non-negative. So summing up, we know that this is at least n minus 1. Okay. So if there exists a non-free rational curves on X, then its anticanonical degree is too large. And furthermore, from the viewpoint of the deformation theory of rational curve, this means that the locus of the family of rational curves containing this C, non-free rational curve, is very, very large. So this is a very strong condition. So I will explain, I will use this later. So this is a second lemma. And the third lemma is the following. So let phi be a morphism from X to Y, and assume that this phi is a smooth morphism with irreducible fibers. Then the following hold. So the first assertion is if the dimension of the base manifold Y is at least 2, then Y also satisfies the same condition as X, which means that the secondary exterior power of the tangent boundary is F. And furthermore, if the dimension of Y is at least 1, then any fiber admits F tangent boundary. Okay. This can be seen very easily by using the fundamental argument of the short exact sequence. Anyway, I will use these three lemmas. Okay, so by using these three lemmas, so let's go into the proof of the theorem A. So as I explained, theorem A is the following. So let us first consider the first assertion. Okay, so to prove the first assertion of theorem A, let X, so assume that X admits a birational contraction phi over Kx negative extreme array R. Then what I need to prove is X should be the blow up of the projective space at that point. But yeah, again, I have no time. I have no enough time to explain the detail. So I want to explain how to narrow down the possibilities of the type of birational contraction. Okay. So then let us recall the following proposition, which is nothing, which is Ionescu-Wisniewski inequality. So I want to apply the inequality for our case. So let phi be our birational contraction here, and then let E be the exceptional locus of phi, and let F be an irreducible component of a non-trivial fiber of phi. Then we have dimension E plus dimension F is at least dimension X plus length of the array R minus 1. So what is length? As you know, length is the minimal value of the anti-canonical degree of rational curves in R. Okay. And then, as I explained short time before, any rational curves in the array associated to birational contraction is not free. So we can apply the second lemma. We know that our length LR is at least n-1. So this followed from the second lemma. Then, by applying this Ionescu-Wisniewski inequality, we have this is at least n plus n-1 minus 1. So this is equal to n-2. On the other hand, we have an upper bound of this guy. Actually, now we assume that phi is of birational type. So E is, of course, E is proper subset. Okay, proper subset of X. So the dimension of E is at most n-1. And furthermore, F is also contained in E. So it means that the dimension of E is, again, at most n-1. So as a consequence, we know that this is at most 2 times n-1. But these two numbers are the same. So as a consequence, we know that the dimension of E and dimension of F are equal to n-1. So this means that our contraction should be the divisorial contraction. And furthermore, we can check that E is equal to F in this case. And then it means that the image of E by the contraction phi, so say phi E, is a point. Okay. Okay, so then by using some classification result of the contraction, we can check that phi is a blow up of some manifold Y at a point. And then we can narrow down the possibility of Y by using some computation. And then finally, we can check that Y is a projective space. So X is a blow up of Pn at a point. So this is a rough idea how to prove the first assertion. Okay. And so let's go into the second assertion of the theorem A. So to prove the second assertion, assume a contraction of K negative extremal array phi is of fiber type. Then I want to show that phi is a smooth morphism. So to prove it, so take a minimal extremal rational curve C in R and take a family of rational curves M, which contains C as a member. Then, so we have three guys, these three guys. And then there are two possibilities. The first possibility is any M curve is free, and the second is there exists a non-free M curve. Yeah, and in the first case, as I explained, we may prove that phi is smooth by the same way as the Maripeta and Schneider, Wisniewski, and Kanevitz. Yeah, actually, in this case, our contraction coincides with rationally chain connected vibration with respect to our family M. And then, so by the theorem by Kanemitsu, we can show that our contraction is a smooth morphism. And in the second case, so by the second lemma, as I explained, we know that the range should be at least n-1. And as I explained, then the locus of the family M should be very large. So from this argument, we can show that the dimension of the base manifold Y should be at most 2. So then by case analysis, we can also check that in this case, phi is also the smooth morphism. So this is a rough idea. The point is, so if there exists a non-free M curve, then the anti-canonical degree should be very large. So this is a point. So as a consequence, we can get a theorem A. And by using this, I want to explain how to prove the theorem B. So the statement is as follows. So if X is rationally connected, then X is a funnel. And furthermore, its Kramer-Morricone is a simplicial form. So how to prove this? So let me explain the outline, how to prove this. So we proceed by, we prove this by induction on the Picard number. And when the Picard number one case, the statement is trivial because the rationally connected manifold of Picard number one is of course a funnel. So we may assume that the Picard number is at least 2. And then by theorem A, if X admits a birational contraction of an external array, then we know that X should be the blow up of the projective space at a point, but you know it is the blow up of Pn at a point is funnel. So we may assume that any contraction is smooth by theorem A. And then remember the following lemma 3. Basically, so roughly speaking, lemma 3 tells us that the target of the smooth morphism also satisfies this condition. Okay. So our X satisfies these two conditions. The first condition is the second extreme power is F, and the second is any contraction of extreme array is a smooth morphism. So then, how to proceed? So take a smooth contraction of a kx negative extreme array, say phi 0, from x to x1. Then by lemma 3, we can check that the second extreme power of the tangent bundle of x1 also is also NF. And furthermore, we can check that the second condition of here also satisfies. So x1 also satisfies this condition. Then again, we can take smooth contraction of kx1 negative extreme array, say phi 1, from x1 to x2, and then x2 also satisfies the condition star. Then by doing the same procedure repeatedly, we can obtain a sequence of smooth contractions of a k negative extreme array like this. And in the end, this y satisfies these two conditions. That is, the secondary extreme power of the tangent is F and Picard number is equal to 1. Then of course, y is a funnel manifold. So let us consider the composition of these contractions, and we denote it by F. So F is a morphism from X, F is a contraction from X to Y, and Y satisfies these two conditions. Okay. So we have this contraction. And then, so take any point, small y on Y, and then consider the fiber large F of small y by F. Then we may prove the following. The first is any fiber large F is a funnel with F tangent bundle. This follows from the inductive hypothesis, and this also follows from the lemma 3. And furthermore, then this is a smooth morphism with irreducible fibers, and any fiber is a funnel. And furthermore, the target Y is also funnel. From this, we can show that the Picard number of F is equal to rho x minus 1. And then by induction, we know that the Kramer-Morris cone of F is Simplicia cone. So it means that there exists a rational curve C1, C2, C low minus 1, such that the Kramer-Morris cone is generated by these guys. Okay. And then, so this can be seen as a vertical data of the structure of this X, okay, with respect to this morphism. This is a vertical data. Then I want to know the horizontal data with respect to this F. So to know the horizontal data of this guy, so let us consider a rational family of rational cars on Y. Okay. Since Y is rationally connected, more generally, this is a funnel. So this is covered by rational curves. And then, so take a rational curve with minimal anticanonical degree. So which is denoted by L here. And then, so as I said, any fiber is funnel. So in particular, these are rationally connected. So by applying the theorem by Graber-Harris-Stahl, we can construct a minimal section with respect to this L. Okay, so this L can be lifted to X. So this L tilde is a minimal section. Then consider a family of rational curve M which contains L tilde. So this is nothing but the family of minimal section with respect to this F and minimal rational curves on Y. Then from the minimality, we can check that our M, the family M, is unsplit family. And then we can consider the rationally chain connected fibration with respect to this M. And furthermore, we can check that this is a smooth morphism. Basically the same way as DPS, SW, and Kanemitz, the result. So by this argument, we can construct morphism from X to Z. This is also a contraction of an extremal array. Okay. And by the inductive hypothesis, we know that the Kramer-Morris cone of Z is simplicial because this is a smooth morphism and the target also satisfies the naifness of the secondary state power of the tangent. Yeah, and this is a rational connected, so this is a funnel. And by inductive hypothesis, we know that Z is also funnel, and the Kramer-Morris cone is simplicial. And we can also see that the Picard number of Z is equal to rho x minus 1. So then, as I said, rho f is also equal to rho x minus 1. So the Picard numbers of F and Z are coincide with each other. And furthermore, this psi does not contract any curve in the fiber large F. Then by using this, we may prove that this natural morphism is an isomorphism. So, and furthermore, the Kramer-Morris cone of F goes onto that of Z by this isomorphism. And as I said, the Kramer-Morris cone of F is spanned by Ci's, and then we have the Kramer-Morris cone of Z is spanned by these guys. Then by using, because this is a contraction of extremal array associated to the minimal section. And then by using this, it's easy to check that the Kramer-Morris cone is spanned by these guys C1, C2 data C low -1 and the minimal section. But as you know, these guys have positive anti-canonical degree. So by applying the Kleiman's ampleness criterion, we know that the anti-canonical divisor is ample. So it means that X is a fan. And furthermore, we can also know that from this, we know that the Kleiman-Morcon is simply shallow. So this is the outline of the proof of theorem B. And finally, by using this, I want to go to the proof of theorem C. The statement of the theorem C is the following. So if the second exterior power of the tangent boundary is nef, but Tx is not nef, then X should be a Fano manifold. So actually, as you know, there is a structure theorem of project manifold with nef anti-canonical divisor due to Cow and Ehring. What they proved is the following. So for project manifold with nef anti-canonical divisor, there exists a locally trivial fibration X to Y, such that the fiber F is rationally connected, and the canonical divisor of Y is numerically trivial. So let us apply this theorem. So let X be a project N4 with nef second exterior power of the tangent. Then, as we checked, anti-canonical divisor is nef, so we can apply Cow and Ehring theorem. Then we can get a locally trivial fibration like this. Okay, then it's easy to check that from this we see that the tangent bundle of Y. It's easy to check that tangent bundle of Y is numerically flat, and then we can construct an ether cover such that Y tilde is an aberrant variety. Then take this fiber product like this, and furthermore, we can check that if the dimension of Y is positive, then we can show that Tx is nef. So this implies that the dimension of Y is equal to 0, and then by the theorem by Cow and Ehring, the fiber should be rationally connected. But as I said from the theorem 2, sorry, this should be theorem B. From theorem B, X should be a Fano. Okay, so as a consequence, we know that the theorem C holds. So anyway, so these fives are the main results of my talk. And okay, I stop here. Thank you.
Thank you very much. Okay, thank you for the talk. Okay, do we have any questions? Any questions? Okay, so if not, I'll ask a question. So about this corollary E,
Yeah.
I mean, what is it that you expect? What is the main thing that is missing to get the higher dimensional version? I mean, higher dimensional.
Yeah. To prove corollary E,
Yeah.
we need to use the result of the Campana-Petane conjecture. As I explained, the Campana-Petane conjecture holds for dimension at most 5.
Right.
But to prove this corollary, we need this. We need the Campana-Petane conjecture. So that is the point. If we can, yeah. If the Campana-Petane conjecture holds, then we can generalize this result.
I see. So there's no reason. So if that holds, then this holds without any restriction.
Yeah.
I see. Okay. Okay. So any other questions? Well, if not, let's thank the speaker again. Thank you very much.
Thank you very much, everyone.
Apologies again for being late. So let me stop the recording.